One of the present generally conspicuous physicists, Michio Kaku, has talked about his assessment concerning this issue. Kaku, known for his astounding contributions to the field of physics, has recently acknowledged that the James Webb Space Telescope, JWST, has discovered 6 monstrous, inestimable systems that researchers once thought couldn't exist. These appraisals have the potential to open up new perspectives in our ongoing appreciation of the universe. It is therefore entrancing and worth observing these changes. Kaku is an extraordinary figure in the scientific field, a physicist of American and Japanese heritage. He is viewed as an expert in both traditional exploratory physics and quantum mechanics. Unlike some more moderate and suspicious researchers, Kaku doesn't belong to that group. He has been open to the astonishing new findings of the James Webb Space Telescope mission. We are grateful that this distinguished researcher has decided to end his silence and share what can no longer be denied. The excitement and enthusiasm of the famous physicist are clear in his remarks on the discoveries made by the JWST. Given that this has been the feature that has sparked his interest, join us to explore the implications of Michio Kaku's disclosure of these 6 gigantic inestimable systems. Kaku is a researcher who has always been able to contemplate new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku recognizes that the discoveries of the new telescope could potentially improve the scientific field, although many of his colleagues have not been able to adopt this view. It is causing concern and restlessness among defenders and critics of quantum mechanics. Nonetheless, this only invites laughter from Kaku. The JWST has uncovered the discovery of 6 gigantic universes dating back to the earliest epochs of the universe. Each of these grandiose systems contains more stars than our own, despite having formed only a brief time after the Big Bang. The group of cosmologists who made the discovery has named these magnificent systems universe breakers, as their presence would change our entire understanding of the universe. Something here no longer fits with the theory of the Big Bang, which tells us that the universe was a disaster area after the initial event. The first solid objects took hundreds of millions of years to form, and it took countless more years for objects to reach a useful density and produce light. The development of complex structures like galaxies should have occurred much later. Some of the newly found systems surpassed the Milky Way in size, and their immense brightness shows that they were likely forming many new stars every year, whereas our galaxy forms stars only intermittently. It remains unclear exactly when the first galaxies formed. Scientists had been unable to determine this until recently. The only thing that is clear is that initially, there may have been only single stars or groups of stars that eventually came together to form progressively larger structures, ultimately leading to the formation of dwarf galaxies, which merged and gradually evolved as previous theories had predicted. Incredibly, massive and large galaxies could not have existed at that time, which raises the question of whether the universe is much older than previously acknowledged or whether complex toroidal structures were formed much earlier than anticipated. This situation is challenging for conventional science, which still struggles with this model. Moreover, some areas of physics have strongly rejected this discovery, pointing to potential errors in the age computations. Kaku was aware of this and had this to say: "There are many instances of old and misleading theories that persist due to the prominence of certain researchers. Many of these theories were eventually disproven when fundamental research revealed their false ideas. Therefore, the key work in any science, particularly in physics, rests with the experimentalists who maintain the integrity of the research. As a matter of fact, on Earth, we have virtually no information on the true origins of the universe." The Big Bang theory was formulated in 1927 based on observations of the universe's expansion. This led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists still face challenges in understanding it. However, it is crucial to reconsider these possibilities. These new insights don't fit at all with what scientists have relied on for years in the Big Bang theory. But science has shown time and again that reassessment and openness to groundbreaking ideas are critical components of the scientific process, just as much as the validation of specific theories and observations. When Einstein was a young man, It was believed that the stars and planets were firmly fixed in the universe and that these particular structures occupied a defined space. However, we now understand that everything in the universe is in motion. Planets orbit stars, stars move within their galaxies at various kilometers per second, and entire galaxies move rapidly through the universe, the fate of which we cannot yet predict. Today, scientists are challenged to accept uncomfortable findings, and it is understood that theories are not simply assumptions or fundamental truths until they are thoroughly tested or confirmed by accurate observations. The idea of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is relative to the distance from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a long time, parts like cosmic microwave background radiation and the redshift of light from distant galaxies seemed to support this theory. However, it is important to remember that in the past, people who believed the Earth was flat and that the Sun orbited the Earth also had this kind of evidence for their doubts until events or technological advancements provided a clearer and more accurate picture. Right now, we are seeing a similar situation. Scientists expected the new JWST to confirm the assumptions associated with the Big Bang, but instead, they have encountered the six systems that appear far too advanced for their age. This reminds us that science is continually evolving and that scientists must be open to new discoveries and reconsider existing theories in light of available evidence. Researchers use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, you can imagine stopping and listening to a car coming towards you. As the car approaches, you hear the engine get louder. However, once the car passes you or moves away, the engine sound changes. This is because the sound changes as the car moves. The same is true for light. When a light source, such as a distant star, moves toward us, the light we see shifts toward blue tones. Conversely, when the light source moves away from us, the light shifts toward redder hues. This phenomenon is called redshift. Physicists have converted redshift values into speeds and distances for measuring sums in the study of the universe. However, it is important to note that small errors in these measurements can have huge implications. The measurement techniques previously used are now under review, and the results that experts will arrive at concerning the latest discoveries related to our universe are intriguing. It is essential to consider whether these results are really based on redshift errors or whether some experts are simply denying the facts. This is a question that requires intensive evaluation and careful scrutiny of the data and techniques used in the study. As scientific inquiry progresses, the discoveries made by instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The new discovery of 6 massive inestimable systems dating back to the early stages of the universe is one such example. These systems, which defy conventional hypotheses of galaxy formation, raise significant questions about the timeline and processes associated with the development of large structures. The James Webb Space Telescope, a replacement for the Hubble Space Telescope, is equipped with cutting-edge technologies that enable it to peer deeper into space with exceptional clarity. Its ability to detect light from the far reaches of the universe provides space scientists with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models, which predict that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, compelling scientists to reconsider established theories about the early universe. This includes the hypothesis of the universe's beginning, which states that the universe began from a single point and has been expanding ever since. While observational evidence like the cosmic microwave background radiation and the redshift of distant galaxies initially supported this hypothesis, the discovery of galaxies that appear far too evolved for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has commented on these developments. Kaku, known for his ability to connect complex scientific ideas with public explanations, recognizes the profound potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the idea that groundbreaking observations should prompt revisions in scientific thinking. He has emphasized the importance of empirical evidence in shaping our understanding of the universe, highlighting that theories must continuously evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are supporters who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic development than previously thought. This perspective challenges the traditional view that galaxies evolve gradually over billions of years through mergers and the steady growth of smaller objects. On the other hand, skeptics caution against discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the surprising findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these key investigations. As galaxies move away from Earth, the light they emit shifts toward longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy spectrum, astronomers can infer its distance from Earth and its speed relative to our own galaxy. This information is essential for constructing models of galaxy evolution and understanding the distribution of galaxies throughout the universe. The James Webb Space Telescope's ability to detect faint infrared signals allows it to observe galaxies that are otherwise obscured by dust and gas in the early universe. This capability is crucial for studying the formation of stars and galaxies during the universe's infancy, a period known as the cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that led to the formation of the first stars and galaxies. In addition to its astronomical implications, the discovery of these early massive galaxies raises philosophical questions about the nature of scientific progress and human understanding over time. Scientific paradigms have shifted in response to new discoveries and observations. What once seemed impossible or too speculative to establish as theories eventually becomes accepted as new evidence emerges. This iterative process of theory, observation, and revision is essential to the advancement of knowledge in all scientific disciplines. The concept of a paradigm shift, as described by philosopher Thomas Kuhn, illustrates the profound change that occurs when anomalies in existing theories prompt a major reassessment of scientific principles. The discovery of early massive galaxies urges cosmologists to rethink their understanding of cosmic evolution and the processes that led to the galaxies we observe today. It underscores the importance of remaining open to revolutionary ideas and revising theories in light of experimental evidence. Cosmologists and astrophysicists are also grappling with the implications of these discoveries for our understanding of dark matter and dark energy. These elusive components, which together account for a significant portion of the universe's mass and energy content, play a crucial role in shaping the large-scale structure of the universe. The distribution of galaxies and the rate of cosmic expansion are influenced by the gravitational effects of dark matter, while dark energy is thought to drive the accelerated expansion of the universe. The discovery of early massive galaxies places new constraints on theoretical models of dark matter and dark energy, prompting researchers to refine their understanding of these mysterious phenomena. In the realm of theoretical physics, the discovery of early massive galaxies has sparked renewed interest in alternative cosmological models. Some theorists propose modifications to the standard cosmological model, such as the introduction of extra dimensions or changes to the laws of gravity, to account for the observed anomalies. These theoretical ideas challenge physicists to explore new avenues of inquiry and develop novel theoretical frameworks that can accommodate both established observations and emerging data. The JWST discoveries also have practical implications for future space exploration and the development of advanced astronomical instruments. By pushing the limits of observational capabilities, the telescope provides valuable insights into the technical challenges of studying distant galaxies and other cosmic phenomena. It serves as a testament to human creativity and the collaborative efforts of scientists, engineers, and technicians who design, build, and operate cutting-edge space observatories. Looking ahead, astronomers expect further revelations from the JWST that will continue to reshape our understanding of the universe. Future observations may uncover additional early massive galaxies, shedding light on the diversity of cosmic structures and the processes that govern their evolution. These discoveries will inform ongoing efforts to unravel the mysteries of cosmic evolution and deepen our fascination with the intricate dance of physical forces that shape the universe. In conclusion, the discovery of early massive galaxies by the James Webb Space Telescope represents a major milestone in our exploration of the universe's origins and evolution. It challenges existing theories, raises new questions, and highlights the dynamic nature of scientific discovery. Michio Kaku's perspective on these developments underscores the importance of embracing uncertainty and remaining open to groundbreaking revelations as humanity continues to probe the mysteries of the universe. Each new discovery brings us closer to unraveling the vast tapestry that surrounds us.